Thanks for joining us there on Zoom, everybody. I can see there's an audience here tonight online, and we've got quite a large crowd here at the clubhouse tonight. So without further ado, we're a bit delayed starting. I'm going to hand over to Mark, EI4ACB, on this talk about SDR, and we'll let Mark screen share and go ahead from there. Okay, thanks, Mark.
Good evening, everybody. My name is Mark, EI4ACB, and thank you for some of these people coming around this evening to software applied radio. Okay. So just a quick overview of what we'll talk about. First of all, make a start by taking a look at what currently happens in analog, what digital is actually trying to do in terms of replacing some of the analog pieces. And then we're going to look at the definition of SDR radio. So then I want to say something about the fundamentals of software defined radio. There's only three things you really need to know. They take a bit of getting the head around, but once you sort of get it, they should be able to any SDR radio and understand what's actually going on. Some of the stuff might actually sound counterintuitive, but as I said, hope you have a few examples that you will actually be able to appreciate, what it is the fundamentals relate to. But as I said, once you do get it, hopefully you will, you have no problem understanding how SDR would work. And the three are basically signal conversion, which is basically analog to digital conversion. Sampling, and particularly this concept of the Nyquist zone. Okay? And this leads to an important concept known as undersampling, which actually allows to sample very, very high frequencies. Then something which a lot of people have struggled with is something called IQ signal representation, something called the quality representation of signals. And then I'm going to have a look at basically how SDR architecture has evolved. So a lot of the technologies moved on, and certainly I suppose the equipment is becoming more and more powerful in terms of processing power for SDR radios. You can do a lot more, and that's also had an impact on the architecture that's used. We look particularly at some of the different generations of SDR architecture. And hopefully then I'll finish off with some examples and demonstrations. So I've brought some of the popular ones along, so you may see some of these, like HackerF is one of the very first ones, the good old RTL, the SDRPlay, which is what you have. You know, why not be so familiar with, so I can read a bunch of stuff here, what I do. This is the current price here in that West Radio that I have. And this is new one as well, which uses something called an FPGA. The same one, but going to get demonstration. Just to be clear, this talk is going to focus on the RF front end and sampling. So each state part of SDR. There's what's sometimes known as the dongle, this part, and there's the program that runs it or that supports it. That's not, I will not be looking at the programs. Well, I'll introduce them, but I won't be explaining anything about them because to actually explain the DSP techniques, I simply wouldn't have time in this talk, but maybe for another day. But I'm going to focus mainly on the dongles and what they actually do in terms of sampling. So hopefully you're all familiar with the classic analog receiver. This has also been around since the 1930s, developed by Edward Armstrong, the man who also is credited with inventing FM. And but he actually had the first patent on this back in June 1920, so it's been around for a long, long time. But the idea is very, very simple. Like you can down convert all the RF signals to a fixed intermediate frequency, where then you do further filtering and also modulation. And this is really the classic radio design, and this is known as the band pass signal. This is what actually goes out on the air. And then at the far side receiver, you need to down convert, and then we'll drop it back down and recover the baseband signal. This baseband signal can be voice, it can be video, it can be data, whatever it is that you're looking to carry. So it doesn't matter whether it's an analog to the digital signal. This is known as the baseband signal. You then move it up the carrier, the transmission, bring it back down again to receive and recover it. I'm hoping to simplify I'm hoping to optimize the filtering. They use an intermediate frequency, or known as an IF. This allows you to use fixed filters. So in other words, you have very, very good rejection of other signals. And so it just greatly simplifies the overall operation device in terms of filtering. The important part of all of this processing is done using analog circuits. Okay, so everything here is basically involved with things like mixer, transistor mixers, effect mixers, filter capacitors, and resistors and inductors. Okay. All that is sort of changed under the SDR paradigm. But under SDRs, And this was actually first proposed by a guy called Joe Mottola back in the early 1990s. And he envisaged a radio receiver, a radio system that looked like this. Okay, but basically, as soon as possible, you turn the analog RF signal into a digital signal. All the signal done, all the signal processing in terms of filtering, demodulation, tuning, and so on, is all done using software, or at least software that's running on configurable hardware. Okay? And eventually, then, for the purposes of recovering the original signal, you have some digital to analog conversion, so you basically get the analog signal, you recover the analog signal off the carrier. And vice versa for transmitter, it's the other way around. You basically take in some sort of an audio signal, or an analog signal, do audio processing digitally, and then push it up then to the final stage where you turn it back into an analog signal, put it out onto the antenna and out onto the air. So the key thing about this, all signal processing is done digitally, either in software or also seeing hardware. So these type of devices here, there's a lot of this done when it comes down to hardware. And this is supposed to be an FPGA device. And I'll say more about this in the demonstration. The key thing about all this is that this really is a new class of radio that can be reprogrammed and reconfigured through software. There's no need to touch the hardware in any of this. If you want to change anything, you just go in, you change some parameters, you program, or use a piece of upgrade your firmware, or whatever you're doing. It's very, very simple changes are required to either change the mode, change the band, change the electrical regime, whatever you're going to do to radio, can all be done in firmware through a software update. You do not have to go in and start messing around inside the box and changing your components and so on. So, in terms of the definition, as I said, the first people started looking at SDR, the American military, that comes out the fact that it's very deep pockets. But particularly the US Navy had a system called Speakeasy 2. It was one of the very first software defined way that was used in military communications. And this is sort of prompted obviously a lot of research. Minnesota Navy was declassified, and we're going to sort of into the general civilian world. The IEEE, which is the professional engineering organization in the United States, they have a group that sort of looks at all different aspects of SDR, and particularly trying to regulate a bunch of defined standards around it. So they came up with a working definition that says this is radio, in which the sum of all of the physical layer functions are software defined. And what the key thing about this is it basically defines the collection of hardware and software that is modifiable, okay, using programmable processing technology. So the whole thing here is flexibility, ease of modifiability, ease with which you can modify an operation, you can modify the frequency range, modify the load, modify every aspect can be done without having to mess around with the hardware. It's all done using software. And also more recently, the new generation of devices called FPGAs, or field programmable gauge arrays that come in. And these are based on hardware, a chip that can actually be reconfigured. So, for example, if you basically want to upgrade firmware in Icom 7300, what you're actually doing is you're upgrading the firmware through reprogramming the FPGA. Again, it's a completely flexible these devices. But as I said, they're actually using Icom 7300, also using this device here, and the same order that you get to it. So the whole thing here is really all about configurability and programmability. The idea that you don't have to mess around the hardware anymore. It's all basically done through software. Now, the main driver for all of this is basically that in the last 20, 30 years, you get a massive increase in the performance, but also the reducing costs of the various enabling technologies. So, for example, analog to digital converters are now very, very powerful. Same with the GTA or digital to analog converters. Also, it's not possible to have processors built into the radio as well. So there's a microprocessor in this device here, actually built into the FPGA. Okay. And also, of course, Moore's law is going to help us. Moore's law basically states that the power of a processor basically doubles every 18 months. And so, remarkable law that is, we keep saying it's coming to an end, and we still manage to squeeze performance out of it. So it's one of those remarkable things that that exponential growth that you see in computing power using more and more radios, and it's just getting cheaper and cheaper and cheaper. So this is one of the reasons why she's one of the main drivers for all this technology. So the main benefit is their flexible, I suppose, functionality. And the nice thing is the operation of the radio can be changed without having to make any physical change, the physical operation of the radio. You just need to go in and reprogram either the hardware or maybe reprogram the software. This makes it very, very attractive. They're building radios in different regulatory regime. You don't have to build a different radio all the time. So the standard radio, this happens a firmware that's used by Europe, firmware from America, framework from Asia. They don't have to constantly have to work on all these. People always get hardware versions done. So I suppose the key aspect of all this, as we saw, the chart was what you need to do first of all is to turn an analog signal to digital signal. This is the digital conversion. And this what this involves is taking in an analog signal and turning it into a binary signal, which in this case is just a string of binary ones and zeros. Okay. And I also want to make sure that string of ones and zeros, I suppose, represents the signal that we're actually trying to process. And there's two distinct aspects to this digital conversion. There's the analog to digital bit. Then obviously there's the reverse bit, which is the digital back to the analog. Okay. Now by far the analog to digital is the most difficult bit. Digital analog is relatively straightforward compared to analog to digital conversion. So analog to digital conversion, what it's really concerned with is how to convert an analog signal to digital signal without losing any information. That's the tricky bit. Right? There's no point that I converting it into digital signal if it's a very poor representation of signal we're trying to process. So analog to digital conversion actually involves three processes: sampling, quantization, and encoding. And they're sometimes collectively known as PCM or pulse code modulation. It's actually a British invention. The event was shortly after the war. We'll see people maintain that the technology has actually been used during the Second World War by the British and the Americans as the early form of digital communication. But basically what it means is you can take in a digital signal, any digital signal, any analog signal, and turn it into a digital signal. Three distinct steps: sampling, quantization, and encoding. So the first thing is you want to basically sample it. And this basically means involved taking a series of regular space samples. Okay. And what happens then is you have to quantize that because those samples can have an arbitrary levels, and you need to fix them to a finite number of levels. And that level then, each of those levels is encoded using a unique binary code word. So in this case here, you can take in an analog signal, sample it, quantize it, encode it. You can turn it into a string of 1 and 0s at the output. And this is what DSP, or digital signal processing, works on. It works on the digital representation of signals. So pulse code modulation, this is a diagram sort of explains what's going on. So the first thing is we basically just need to sample the signal. So we don't follow the signal at all time. You basically take a series of regularly spaced samples, TS seconds apart, and also the sampling rate is 1 over TS. Now each sample value needs to be quantized and it's round off to a nearest quantization level. And that basically then is represented by the unique code word. So for example, if you were using a technology or a system that had a 3-bit code word, you know, 2 to the power of 3 or 8 possible levels. And that's a very coarse level we have to represent the signal. But as quickly you move up towards 10-bit, 12-bit, 14-bit, and even 16-bit analog to digital converters, you see, you now start having tens of thousands of possible levels. And that gives a very fine resolution. So you can actually have a very high degree of accuracy in actually representing that particular signal. So the problem with quantization is that unfortunately it's not perfect. That rounding off basically means you've lost information, and unfortunately it's irreversible. You cannot recover that rounding off of the receiver. And that's why sometimes known as quantization noise. It's specifically a form of noise. So I suppose the good news is that as you use more and more and more bits, basically the signal to noise ratio from that quantization noise gets bigger, at least the sort of ratio improves. The impact of noise gets smaller and smaller and smaller. It's sometimes known as the 6 dB rule. That roughly means that your signal to noise ratio increases at a rate of 6 times n, where n is the number of bits that you use on a digital converter. Okay. Furthermore, the dynamic range, which is the difference between the smallest signal and the largest signal, is basically approximately 6 times n, where n is the number of bits. So, for example, if you're using, for example, a 16-bit analog to digital converter, you've got 960 dB range on the receiver. That's the colossal range. That's the difference between the weakest signal and the strongest signals that can be commonly. There's also a technique as well, something called dithering. And dithering means you deliberately introduce noise. And what that basically does is it basically helps you to minimize, or what it actually does is it breaks the link between the quantization noise and the signal. So it makes that quantization noise like pure noise, or what you call adequate Gaussian noise, because it has a minimal impact on the signal. So if you've ever been playing around with SDR radios and you see the dither button, it's only going to be to turn it on. because it will improve the signal noise ratio, it will also improve the dynamic range of your receiver as well. So generally, basically, it's deliberately introducing noise to basically try and mask out that you sort of smear out a quantization error. So the other big question is okay, we could talk the quantization, so how fast should we sample? How many samples do you need to take per second? So the public hearing comment is, well, maybe we take too many samples, that means excessive computation. We take way more samples than we need to take. That means there's a lot more processing involved. We're overdoing it. On the other hand, if we take too few samples, we're probably going to lose information. And this problem was actually solved back in the late 1920s by probably the two biggest names in the whole area, certainly digital communications, Harry Nyquist and Claude Shannon. Harry Nyquist is also the engineers of the oil, and Claude Nyquist, of course, is best known for a lot of working on stability of electric circuits and electronic circuit amplifiers and so on. And Claude Shannon, of course, is famous because he basically is the man that basically created the modern information age. He actually quantified what information means. He came up with a brilliant paper in 1948, basically. He created a whole area of self-known information theory. And Claude Shannon, I suppose, electronic and communication engineering with Einstein to physics. That's his contribution. That's how monumental it is. Unfortunately, most people don't know about him, but he's actually an extraordinary character. He extraordinary insight into what he did with his contribution he makes to the field. But anyway, they came up with a theorem that said it tones how fast we need to sample. So basically says that any signal can be represented by a series of discrete samples, provided you sample at least twice the bandwidth of the signal. So, for example, if your signal is 10 kilohertz wide, you need to take at least 20,000 samples to capture all the information. And what it means is there's no loss of information here. You might think because of the gap between the samples, you're somehow losing information. They're not. It's all the information is absolutely intact. That one of the remarkable findings was that nothing happened. What this out. So that's the important thing to remember here is that you need to sample at least twice the bandwidth of the signal. Or to put it another way, because it tends to work the other way, you tend to sample at a fixed sample rate. What that basically means, the maximum bandwidth that you can accommodate is half the sampling rate. So if you're basically sampling, say, 10 megabits per second, that's right, but you're sampling 10 million samples per second, the largest bandwidth, the largest chunk of spectrum that you can look at is 5 megahertz. Okay, so that's a number to always remember. It's always half. Okay, half the sample rate. So you come across in the literature and read any literature, you get any of these devices here. We don't tell you what the sample rate is. You know, the 10 megasamples per second is 100 megasamples per second. The first thing you do is in your head is divide by 2, and that will tell you the chunk of bandwidth you can look at. So that's the chunk of spectrum you can actually digitize, if you like, using these devices at the sampling rate. So the question then, of course, is, well, what happens if you don't sample that? We don't sample fast enough. Well, you get something called aliasing, which effectively is known as spectral folding. And this is one of the quirky things about sampling. What it means is that all the signals effectively get folded back, or sometimes known as alias, back to the frequency between 0 and half the sampling rate. So in this particular example here, you can see that in the case that we're going to have the frequency here, 180, that gets basically folded back to 20, and the signal 310 gets folded back to 90, because all this is folded back. It always gets folded back to the sampling frequency. And the way you avoid that is you have to do something called an anti-aliasing filter. And this basically means and you find this everywhere, okay? You always find a low-pass filter sitting in front of an analog to digital converter. And what that basically is, that shuts off any signal above half the sampling frequency. Okay? Because you don't want any signal energy that's above that will get folded back down into the part of the spectrum between 0 and half the sampling frequency. It will lead to corruption when it comes to basically reconstruct the signal. But this is known as anti-aliasing filter, and as a low-pass filter always found before the analog to digital converter. Okay? So the best way to illustrate that is the nature of this concept called the Nyquist zone. So the key thing to remember here is half the sample rate. Okay? So what this basically means is you can basically partition up the frequency spectrum, okay, into bands or zones, and they're basically half sampling frequency wise. So this the first Nyquist zone is 0 and a half sampling rate. Second is between half and 1, 1 and 2, and so on and so forth. And provided that this signal can be completely contained within the Nyquist zone, we will not get aliasing. Okay? So this idea of the Nyquist zone is basically, it's based upon your sample rate. You can know what your sample rate is, you divide by 2, that's the chunk of spectrum that you have. That repeats itself. Okay? And whatever signal you have, those that forward back are like alias back down to the low frequency. But let's be clear about this, there's two types of aliasing here. There's good aliasing and bad aliasing. Okay? We're going to look at both, but the good aliasing is where you can actually deliberately exploit this downsample, and basically to down convert from high frequency down to low frequency. This is very widely used. For example, it's used in the Icom 7200. You look at that in a sec. So the best way to look at this is if you imagine you have a fanful of paper. Anyone who remembers the early days of printing would have no problem getting down around this. Paper used to come in big, long legs. So perforating all the pages and perforating also out to there that way. So in this case here, you can consider the frequency spectrum to be a series of Nyquist zones, or if you like, folds of paper, which means they'll have a width or have a bandwidth of half the sample rate. So for example, in the top example here, if you have a signal, for example, that's spread across multiple Nyquist zones, then you basically fold all the paper together and hold it up in light. That's what you basically see. You see all the signals and all the zones all jumbled up on top of each other. And this basically means it's very, very difficult to basically decode the signals. But on the other hand, if you can arrange it in such a way that the signal is only found in one Nyquist zone only, okay, when you collapse all those Nyquist zones down, the only zone that comes through is the one that contains the energy. But the thing about this is, it doesn't have to be in the first Nyquist zone. Okay? So what you can do if you're really, really clever about this, you can arrange it using bandpass filters. For example, in this case here, we arrange in such a way, we use bandpass filters in such a way that we manage to have isolated signal between 1.5 times fs and twice fs, and there's no other signal energy in any unit Nyquist zones. So when you come to basically downsample and you basically come to recover the signal, the only signal that comes through is the signal within that Nyquist zone, but it's been down converted to 0 at the sample rate. So what this means is you can take very, very high signals, and when that you isolate them, there's no other signal in your Nyquist zones, you can down convert them back down to the first Nyquist zone between 0 and half the sample rate. That's a very, very powerful technique. This is one of the reasons why SDRs are used for a lot, for example, in microwave radios and so on. Basically, by using this property known as undersampling. Okay, this is fundamental SDR operation, but bandpass filter is required. If there's any energy system in those other bands, when you come to recover the signal, it all comes down to the first Nyquist zone, and that energy will all get mapped down and get converted down into your reconstructed signal. Okay. So that's the concept of Nyquist zones. It's a chunk of spectrum equal to half the sample rate. And the trick here is to make sure your signal energy is fully contained in just one Nyquist zone. Provided you can maintain that, you're fine. You have no problem recovering the signal. So here's an example of good aliasing and bad aliasing. So in the top example, the signal is completely contained within the Nyquist zone. So when it comes to recovering the signal, it all gets converted down to the first Nyquist zone between 0 and half the sample rate. There's no problem. Unfortunately, the second is an example of bad aliasing. And unfortunately, when the signal energy is linked over, sitting across the boundary of two Nyquist zones. What this basically means is when you come to a recover signal, you're going to get bad aliasing. Okay, which means you're going to get corruption of your signal when you come to final recovery. So undersampling requires that all the signal energy is contained in a single Nyquist zone. And that the width of that zone is half the sample rate. That's all you need to know. Okay, once you remember that, you have no problem understanding SDRs. Any SDR, they all use exploit this particular principle. Now, the other aspect is one that's often is very confusing. I know because students, I've been trying to do this to students for 20 years, and it's still struggling with it, but it's this thing called IQ sampling. It's sometimes known as complex sampling, it's sometimes known as quadrature sampling. Anything SDR uses complex sampling. Okay, or sometimes known as IQ sampling. It's a fundamental concept. What basically, the reason why we do it is it's very computationally efficient. There's a whole series of other processing benefits as well that come from it. I'll say a bit more about those in a minute. But what it means is that a sample has two parts. there's what's known as the in-phase part and the Q part, which is the quadrature part. Now, just to clear that, this quadrature is just a fancy name for 90 degrees out of phase. That's all you need to know. Quadrature, 90 degrees out of phase. And the classic example is the sine wave and the cosine wave. They are 90 degrees out of phase. The in phase is always associated with the cosine. The sine is always associated with the quadrature. So what basically is when you sample, you actually sample, you generate two parts of the sample, a real part and an imaginary part, or what's sometimes known as the in phase of the quadrature part. Okay, and that's really what is happening. You can, I know people often struggle to get their heads around this, but you take it from me. This is used everywhere. There's no SDR in the world. No, I'm not aware of anyone that does not do this. Okay, that's how critical it is. And basically involves when we sample, we create two parts or two parts of the sample, two pieces in the sample. Okay. Now, the reason why we do this, okay, is that all signals can be represented. Basically, what we do with the signal, only two things we need to have in the signal: the amplitude and the phase. That's all we need to have with the signal. We need to know two parts. So there's two things we need to know, two pieces of information we need to have in the signal. And what this means, when we sample, we need to have two parts of information to know the amplitude and to know the phase of the signal. Okay. So in this case here, we can represent the signal, for example, as a point in a two-dimensional plane. The x-axis, if you like, is the in phase and the I part. The y-axis is the Q or the quadrature part. And what it means is a very compact way to represent the amplitude A and the phase angle, which is the angle between the signal and the x-axis. In this case here, it's phi. And you probably asked what about frequency. Well, the frequency is represented by how fast that phasor rotates in the IQ plane. So basically, if it's a positive frequency, it rotates counterclockwise, and if it's a negative frequency, it rotates clockwise. And happy with that? And happy with negative frequencies? Okay, so. I usually have the complaint when I mention that to students. You can look away. This is for the nervous. It's the maxi bit, but it's kind of important. So if you had a horror nightmares in school, don't worry about it. The reason why this is important is that a complex number has two parts: the real part and the imaginary part. And basically, they can be represented in this polar form. I think that's the complex exponential form in terms of amplitude and the phase. And there's a cost part, and there's a famous formula, known as Euler's formula, which basically means you can decompose the signal into the real and the imaginary parts. The cost part is the IQ part, it's the real part, or the in-phase part. The J part, okay, is sometimes called the imaginary part, is also the quadrant part. This is related to the cosine, or sorry, related to the sine part of the signal. So you've got the cosine and the sine, and all signals, digital, analog, audio, or doesn't matter. They've always been represented in this particular two-part form. Okay, it's known as the IQ, or sometimes the quadrant representation of the signal. Okay, and that's really what you need to know about. Again, a horror of maths, don't worry about it. I wouldn't have to say this to those who might be interested in it. It's also worth noting as well that, given my background here, engineers tend to use J, the square root of -1. So mathematicians and scientists use I. The main reason is for engineers, I then use it on curves, so that you want to completely use J. So those are dead given, we need a book. And talk about I, it's for scientists and mathematicians using J is for engineers. So that's how you know that. But anyway, that's the quadrant represents it. All signals, audio, or doesn't matter, can be represented in this way. And this is why we do this when we come to doing it again. We need this in SDR as well. So what this basically means is your cosine wave, if you're just using it in the real signal, as you can see, the series of samples are basically just a one-dimensional signal. Because notice, every time you sample, you just get one value. So for the quadrant representation, you get two values, an I part and a Q part. And this basically here then, as you see, traces out a helix. So basically that helix is spiraling out like this. Okay, and this basically what the cosine wave would look like. And basically, if it's a positive frequency, it's going counterclockwise, and it's a negative frequency, it's going clockwise. And this actually is one of the reasons why SDR radio is used, because if we're using real samples, there's an ambiguity. Look at that signal there. It's not possible to tell whether that's a positive frequency or negative frequency. That's the fundamental problem. you cannot process that using the computer. The computer doesn't know if it is a positive frequency or negative frequency. So the only way you can do that is you can have two parts, the I and the Q. Then it knows this is a positive frequency and this is a negative frequency. And that's really what you need to do. Okay. So that's what cosine wave looks like. That's what an AM signal would look like. So we have to know what an AM signal looks like. The frequency matrix is vary the amplitude. In this case here, this is what it looked like in terms of IQ representation. Likewise, we have an FM signal. You can have another FM signal looks like you hold the amplitude fixed. You can vary the frequency in accordance with the modulating signal. In this case, if the bit light goes down, it's coils in that produces a slinky coils. That's what we have. Where basically we have compressed parts or stretched out parts. Okay. This is the IQ sampling. What it does is it's computationally very efficient, and also said it removes any ambiguity to whether dealing with positive frequencies or negative frequencies. This is very important for SDR circuits to work reliably. Yeah. How do you do it? It's actually very straightforward. Every single SDR circuit that you will ever see, I can absolutely guarantee you will have one of those two circuits, or probably both circuits in it. Okay? You basically have two mixers, and you have a pair of quadrature local oscillator signals. The cost of the sine. Again, the cost of sine and out these interface. So you split the signal into one arm, you basically multiply by the cost. You split it into the other arm and multiply by the sine. That will give you the I and the Q part. So if you want to basically get the IQ components of a receiver, this is what you do. If you want to do the vice versa, you have the transmitter, you want to generate a signal. Again, you take in the IQ parts, multiply them by the cost, multiply by the sine, add them together, and that will give you an EOS signal. Okay. And that's what I said, every signal, whether it's an audio signal, an RF signal, doesn't really matter. Always would be represented by an IQ or a quadrature representation. This is how you would do it in practice. You'd use two mixers with a local oscillator and two outputs, 90 degrees apart of them. Sine and cosine wave. That's how you do it. And so one of the big advantages is that it also allows you to get around, it also actually allows you to change the chunk of sample. So if you're actually doing complex sampling, you can actually go from half the sample rate to the whole sample rate in terms of the chunk of spectrum you can look at. If you think that's fantastic, we're actually grazing there. We actually managed to double up on the curve or then on the digital work. In fact, enough what to do with it. You still the same amount of information. If you have twice as much information, twice the amount of samples here, but half the frequency. At the end of the day, it's still the same quantity of information, but it's more advantageous to do it this way anyway. For the simple reason is it's more computationally efficient and removes any ambiguity that common regular frequencies, which is always a problem behind concept signals. And finally, just to round off a digital to analog conversion. As I said, this is the reverse operation. It's relatively straightforward. Basically, what you do is you basically take in a series of samples. You then you create what is known as staircase approximation, where effectively you hold the value between the samples, and then you use a low-pass filter to knock the edges off and smooth it off. And that's the classic reconstruction filters, as sometimes known as. And this basically helps you recover your analog signal back before the analog digital converter. So just to sort of summarize so far, there's various things we've been talking about. So the first thing anyway is the key feature of SDRs is basically programmability, hardware and software. The main benefit is flexibility. You don't have to fit it on the hardware, you can be programming firmware or just update some hardware that you're using. Analog to digital conversion is very important, particularly with regard to sampling in the microzones. The only thing you need to remember is by and large, you've got the sampling, the chunk of spectrum you look at is half the sample rate if you're using real sampling, full sample rate if you're using complex sampling. Aliasing, there's good and bad aliasing. Good aliasing is where you use a run sampling. Bad aliasing is where you basically don't do your filtering properly. You're going to get corrupted parts of a signal coming in from other microzones coming back to your converted signal. And then the role of IQ sampling, as I said, think of if you really worry about it, is that all samples now have two parts, an in phase and a quadrature part. That's all you need to know. And the way you do it is you use that little circuit there. That top circuit is basically how you do it. That's all you need to really know. That's just the advantages are like computational efficiency and removes ambiguity about the signal. So just to say that, first of all, there's no single definitive architecture that's used for an SDR. You see, they mix and match of everything. But certainly all modern radio uses SDR. So 3G phones, 4G phones, Wi-Fi, Bluetooth, they all use SDRs. Okay? Nobody uses analog radios anymore in terms of modern digital radio. It's so much more efficient to do it using SDR because you can get it on the chip now. It cuts out all the expensive components like inductors, capacitors, filters, and so on. You just do away with all that and just do everything just using SDR, a fast analog digital converter, and a DSP chip. So what we'll have a look now is maybe have a look at how the architecture has evolved in the last, 20, 25 years. And specifically what it comes down to is the capability of the analog to digital converter has basically significantly improved as a consequence of, Moore's law, basically, in terms of the number of samples and also what the sampling rate is. And also more recently, it's not possible all this stuff built onto a single chip. So there's an ORF SoC. SoC stands for basically everything put onto a single chip. Okay, so this is a circuit on chip. You don't have to worry about it after that. You just click all the pins up, the analog bit and the digital bit, and the whole thing just basically works. It's a system on the chip, SoC, and also the advent of FPGAs. So go back to the 1990s. These are the very early days of SDRs. The characteristic of SDRs back then was all the analog to digital converters were slow, relative to nowadays. We could maybe do a few tens, maybe to a few hundreds of kilosamples per second. So they were very, very slow. Okay. And what this basically meant was that most of the down conversion, I guess, was basically done using analog electronics. So you download it, you basically down convert it from the RF down to an IF, pass through a filter. And then basically your analog to digital conversion was basically sampling signals, maybe of a few tens of kilosamples per second. Okay. That's how it kind of work. And likewise, if you were doing the other end in terms of the transmitting end, you would generate signals at a few, these represent generate a digital signal, a few tens of kilobits per second, and then use a digital to analog converter, then turn back to an analog signal, and then up convert it to your carrier frequency and transmit it away. So as I said, this was the early days where it was characterized by the fact that dealing with sampling rates that were certainly below, usually about 100 kilosamples per second, a few hundred kilosamples per second. That was the early 1990s. Now, in the 1990s, the later end of the 1990s, began to sort of improve things by basically using intermediate frequencies as well. So you can also get some of the higher end radios of time where basically used an IF stage. But once again, the basic idea was very, very simple. You're dealing with low bit rate analog to digital converters, usually less than a few hundred kilosamples per second. Okay, this was sort of limiting. This is what limited the performance of SDR radios, the fact that you couldn't deal with very, very high speed signals. So we had to do as much down conversion from a few hundred, a few tens, and maybe a few hundreds of megahertz, all the way down, step it all the way down to maybe a few tens of kilohertz. Then you can start sampling. And that's why there's an awful lot of analog electronics, a very, very small amount of digital electronics. Okay, in the early days, back in the 1990s. Now, in the 2000s, once again, technology marched on, and it was now possible to come up with analog digital converters that work with a few, up to maybe 10 mega samples per second. So it's much, much faster. So what this means now, you can do more processing digitally. In other words, the amount of analog electronics started to shrink. So you didn't have to do so much down conversion from your RF signal, hundreds of megabits to hundreds of megahertz. You only had to step it down to maybe 10, 20 megahertz, okay, 10.7 megahertz type thing. So as I said, the beauty here, as I said, is that the sample rate of the ABCs allows you to basically do more and more in digital. In particular, you see something there called digital down conversion. And this basically means you could actually do down conversion, or known as heterodyning, using digital. So you have a digital mixer, a digital local oscillator, instead of having to do it using analog electronics. Okay, and you can do that because you were sampling so fast. You were sampling in the range of megahertz to maybe a few tens of megahertz. So you can actually do this digitally rather than analog. So in this case here, the amount of analog electronics is starting to shrink, and the amount of digital signal processing is starting to expand. And of course, towards the end of pushing towards 2010, as I said, the ability to manufacture components improved dramatically. So you can now actually start to integrate the analog electronics and the digital electronics onto the same piece of silicon. Okay, again, quite sophisticated fabrication. We then get these sort of mixed signal processing, okay, where you have an analog piece and a digital piece all under one chip. So once again, sample rates in and around 100 megasamples per second. Once again, you didn't have to use separate circuitry. You've got one chip, and with basically a few extra external components, you could basically plug in your antenna, and then get your digital signal out. But once again, notice here this thing called you have destination and interpolation. This is basically digital down conversion and digital up conversion. Same over that in a sec. But once again, this is said as when basically we start to move towards having those RF systems on chips. You go buy one chip that'll basically take in your RF signal and give you digital sample signal at the output. And then a few extra components for tuning and so on, but that's not how it works. And again, many of the designs we look at will actually still use this particular approach. The next one is the one everybody knows. Where what they did was they started putting USB connectors and everything. Okay, so in this case here, once again, sample rates maybe 100 million samples per second. Everything's done using a system on a chip. Again, we use digital IQ sampling. Okay, you can see that there. And also everything now goes to a USB. So all these devices here, USB, which means, but also at the time you see, computers began to become powerful enough that they could actually do all the DSP on them. Up to then, the computer wouldn't have been powerful enough. So the computers have now reached a point, and the USB connections were fast enough that you could actually take in a few tens of millions of samples a second and do all the processing software on your PC. So you get your dongle, plug in the USB connection, load up your SDR program of choice, and you can basically then start doing all your reception and even transmission, basically using a host PC that would do all the DSP piece, and then effectively this is effectively just doing the RF front end bit, the analog to digital conversion, and so on. So, as with all the range we have here, tend to do that. Okay, this is needless to say was hugely popular with hobbyists. So this is where SDR really sort of took off, and lots of people then started going out and buying. The first of them was the Hack RF. And that followed up by this guy. This was in 2014, I think this is about 2015. These were like the early days, and as I said, when the whole thing really started to take off again, there's that USB connection again. So, and then finally we get up onto the real high-end stuff. This is where it's really getting serious. Where actually what we do is, this is go back to what Joe Manoka had intended in the early days. We digitize the signal as quickly as possible. Take in the RF signal, digitize it. We can do that now because we have analog to digital converters that will do 10 billion samples per second. So they're blazingly fast. We can now digitize the signal straight off the antenna, and all the processing after that is done digitally. So all the down conversion, all the heterodiming, all the filtering, all so on and so on, absolutely digitally. Not an analog circuit site, no mixers, no local oscillators. Okay. And an example of that is this particular device here. This is a very, very fast device, okay? And that's exactly what this is. It's a very, very fast front end. Okay. I'll show you this is fantastic. You can actually look at the entire 30 megahertz HF band with this.
Oh, like put a camera there, Mark.
There, yeah. So see, I'll show you more about in a sec. So as I said, there's very little analog processing now, except for that, a bit of filtering at the front end. But that's really about it. Digitize the RF signal as quickly as possible, and everything that is done digitally. So as you can see, as the hardware gets more and more powerful, the amount of analog electronics is shrinking, and the amount of RF processing is expanding, because the processors are now so powerful, and the analog to digital converters are so fast, that we can now do all our processing using digital rather than analog. And these are known as direct digital conversion. And so this device here also does it as well. So just to say something about digital down conversion, digital up conversion, all modern receivers more or less do this. Generally between the analog to digital converter and the baseband processing, there's something called digital down conversion. This effectively is digital heterodiming, where instead of having an analog mixer, we have a digital mixer. Instead of having an analog local oscillator, we have a digital oscillator. and then we have filtering. So this is just what you would used to see in a heterodyne receiver using discrete components. Now it's done using digital techniques. Okay, and once again, if you look closely at it, you see one aspect gives you tuning, so you can have to select the signal of the band you want, and you can also control the bandwidth with a low pass filter. And this uses something called decimation, just make it for more computation. As you drop the signal, you need less and less samples, according to Nyquist. So to save the computation effort, you just throw away some of the samples. Throw away for maybe, you might have 10 samples, but you probably only need every second or third. So you can throw all the rest of them away because the frequency has been dropped. You're not losing anything. That's what Nyquist says. So for computation efficiency, you can throw away samples, but you don't need them anymore. And this just means there's less processing required. So that's at the receiver, you have digital down conversion. At the transmitter, you reverse, you do up conversion. So once again, it's the same thing here. Again, you have a local oscillator that's digitally implemented. You have a mixer that's digitally implemented. You have a filter that's digitally implemented. No discrete, no discrete analog electronic components here. Once again, as I said, the interpolation filter, now because we're going up in frequency, we need more samples. So interpolation means you start filling in the gaps with samples. So you basically interpolate between the sample values, you have to add them in, because according to Nyquist, if you don't, you're going to lose some of your signal information. So it's a technical point, but nonetheless, it is widely used. But every modern receiver you look at will have a digital up converter and digital converter. We haven't looked at some of them anyway. You can actually see how effectively they implement them. And finally, this is sort of an interesting one as well. I suppose in the last 4 or 5 years, there's something called FPGAs. And these are chips that are programmable. So basically, the known as field programmable gate arrays, they sort of turned around the mid-1980s. But the nice thing is that it's an integrated circuit that is configured after manufacture. Generally, if you get a circuit, it's fixed. That's the circuit you get, that's on your chip. Okay. But with FPGAs, there's plenty of design software. One popular is one called Vivado by Xilinx. What it means is you can design virtually any circuit you like, any digital circuit you like, within the capability of the chip, obviously, and you can just flash it onto the chip, and then press that chip does what it was designed to do. And if you decide I want to change the design, you just reflash your chip, and hey presto, it comes up with a modified design. This is very, very widely used in electronics for very rapid prototyping. You don't have to go up to a fab and get them design masks and produce the chip for you. You just get an FPGA, program using the software, flash it on, and hey presto, you have a circuit for prototyping. And basically, it's an example of basically programmable hardware. So, for example, in your Icom 7300, when you every so often, they'll bring out an firmware upgrade. Okay, what they're actually doing is you're actually just reprogramming your FPGA. And really, what it is it's a matrix of basically logic blocks that have interconnections between that are reprogrammable. So basically, by reprogramming the communications between the blocks, you can basically realize any circuit you like. That's all you'd have to worry about, okay? All the details looked after in the software. But typically, modern FPGAs will have probably anything from tens of thousands to hundreds of thousands of these configurable logic blocks. And basically, there's software now that'll do all the hard work for you. In fact, it's like library-based. You just drop components in, it does works on all the detail for you, and then flattens the chip for you as well, And also as well, one of the most popular ones is an FPGA from Xilinx. It's one of their Zinc range. Again, this is an example of an ORF system on the chip. But not only do they have an FPGA, they've got very fast digital to analog converters and very fast analog to digital converters, DACs and ADCs, and also for good measure, they're thrown in a microprocessor as well. So you have an entire radio on a chip, you have a microprocessor to run everything. You've got A to D converters, D to A converters, and you have an FPGA to do all your signal processing as well, all on a single chip. Incredible, And as I said, the design tool called Vivado. So this is what Xilinx is about. Xilinx is probably one of the world leaders in FPGAs at the moment. Okay, so yeah, it's and a lot of their chips. For example, a lot of chips are in the RF we have a look at. So this has a Xilinx chip in it, and also the Icom 10300 has a Xilinx chip in it as well. Okay, so that's what I want to do. Any question by the way, before I go on? What I do now is basically take a look at some examples of everything. Any questions before we?
There's one question from online from Roger. What are positive and negative frequencies? Just talk about
I knew there'd be a question about that. So The better way to look at kind of this is that every signal, okay, so you have to think about signals, you have to think, there's two ways of looking at a signal. You can look at the signal in terms of how it changes in the time domain, or more interesting for communication, if you have that signal, what the signal looks like in the frequency domain. So there's the time domain and there's the frequency domain. They're just two different ways of looking at the signal. They both contain the same amount of information. There's a matter of convenience where you use things in the time domain or look at things in the signal or look at things in the frequency domain. And for communications purposes, the frequency domain is often more interesting because it gives you the spectrum of the signal. You can see where all the energy in the signal is contained. Okay. So if you have any, so generally what happens is if you have a signal in the time domain, and there's various mathematical techniques that allow you to work out what the frequency domain looks like, there'll always be a negative frequency component. So when I say negative frequencies, every signal will have a positive frequency and a negative frequency component. So it's actually called components of the signal, a positive part and a negative part of the signal. Now there's an exception to that called analytic signals, but I won't go into that. They use something called the Hilbert transform, but that's another whole different story. But that basic explanation is that every signal, if you talk about it in the frequency domain, will have a positive frequency part and a negative frequency part.
There's another question here from Rob. I might let him put it to himself, or do you want to take questions at the end?
I can take questions at the end. Maybe.
Yeah, we'll take them at the end. Yeah.
Right, I hope that answers the question.
Okay.
Yeah. Yeah.
SDR. What's a hybrid SDR? And some cases are hybrid SDR.
Never come across hybrid SDR before. That was
The hybrid maybe it's like a mixture SDR.
probably a mixture of SDR. Maybe it's one of those.
What it means is that it has an analog protein. It converts it to
Digital, yeah.
to an intermediate frequency, what you said.
Yeah. It's one of those halfway house radios where, they do a certain amount, you get it down to an IF, and then they do everything. But I would be very wary, this is always a problem have that, there's two types, whenever you look at look at the spec array, you always have to make a distinction between, what is technical talk and what's marketing. Okay. When you see hybrid SDR, that sounds like marketing talk to me. So the marketing guys, they'll tell you like to buy the radio, but be sure about one thing. In terms of technical terms, I've never come across hybrid SDR before. From in a technical perspective, from a marketing and sales, that's probably what it is. That's probably what it is. But it's probably a mixture.
Mark, I know you've been talking mainly about receivers, but I mean, I think you're talking also covered transmitters, using software transmitter. In a software transmitter, would you need bandpass filter?
Yes. Oh, yes. No, absolutely do. I'm going to do that. Talk about it right now. So on that very note, let me start with the first radio I'm going to look at. The ever popular Icom 7300. One for radio. I have one myself. Probably most people in the room here. I probably have one, or else I know someone has one. But it's a fantastic radio. It does HF, it does 6 meters, and does 4 meters as well. It's an example of an RF direct sampling system, which means it basically takes in the RF signal as quickly as possible, turns it into a digital signal. Okay, and does all the processing after that. It uses FPGAs, so it's pretty up to date. And it was actually released in, I think it was that old actually, August 2015. It was launched at the HamPi fair in Tokyo. So it's been around for quite a bit, but it was an exceptional radio. I have myself, brilliant radio. The only slightly shocking thing was it's only when I bought one of those, those little inline power meters you get like an AliExpress for like 20 €20, and I put it in, and I was looking, I said, gosh, I think that's drawing like 1.2 amps. Like that radio and receive, my power and receive draws about 16 watts. Most radios, like analog radios, probably draw maybe 300 or 400 milliamps. This is drawing like 1.2 amps. And you think about it, that's all the processing that's going on. So I suppose the price you pay for all this is significantly larger power consumption, just in terms of driving all this computing power. It's worth just thinking about 16 watt. I mean, that's what this thing works. This is on receive. Okay, it goes up to about 1 over 200 watts, I think, when you go to transmit. Okay, so that's instead is what the Icom. Let's have a close look at the Icom. So the first thing is a picture of a circuit board, and the first thing you see is it has an FPGA. It has a DSP chip, it has a microprocessor chip, and it's got some analog to digital converters. So apologies, it might be a bit small, but it uses is a 14-bit analog to digital conversion, 14 bits. Okay, so multiply that by 6. That gives you roughly what the dynamic range of the device is. But if you look at the circuit here, at both the transmitter and the receiver, as quickly as possible, there's a bit of filtering at the front to answer your question there in terms of transmit and the receive. The first thing you do is turn it into a digital signal, and then do all the processing afterwards using an FPGA and a DSP chip. And it samples at about 124 million samples per second. Okay, so the first thing, hopefully at this stage you're all dividing by 2 in your head. Okay, this is important to see why it is. So roughly, what that basically means is the chunk of bandwidth that you can capture on that is about 62 megahertz. Okay, just hold that number in your head. Okay. So in terms of the receiver, don't worry about the circuit. The only thing I want you to note here is quadrature mixing. Look, the mixer, local oscillator, 90 degrees out of phase. Okay, that's found everywhere. Every single SDR circuit look will have that feature. You should see 2 mixers, a cos and a sine, okay, going in. And the first thing that came to your head is, oh, that's IQ representation signal. That's all you need to know. Don't fret about anything after that. You don't need to know worry about more than that. That's done at the receiver part of it. It uses a digital, or at least like an IF, a digital IF of basically 36 kilohertz. So basically, it's down compared to 36, digital processing at 36. But it's a digital signal 36 kilohertz, it's clear than that. Likewise, at the transmitter, again, don't worry about the circuit. Just look at what you recognize in the circuit. I always say that to my students, like, whenever you look at a circuit, don't be overwhelmed by the circuit. Look at the bits of circuit you recognize. And hopefully you will recognize, look, there you go again. There's those mixers, and there's the quadrature, the cos and the sine. Okay, so there's IQ sampling going on there. That's all you need to know, okay? You also know that that's implemented using DSP chip and FPGA chip. Again, don't really know to worry about anything else. All that's a sort of kind of detail, but just spot the bits you do know. So at this stage, you should be starting to recognize that quadrature. 2 mixers, and the quadrature, the cos and the sine, which gives you your 90-degree quadrature, 2 quadrature carriers that are going in from your local oscillator. Now, let's take a closer look at all this. So I mentioned that it was 124 million samples per second. That means a chunk of bandwidth you can look at with 62 megahertz. Now, this is fine for HF at 6 meters because the HF is all below 30 megs. 6 meters at 50 to 52 megahertz. So that's all sitting below 60 megahertz. So everything is captured in the first Nyquist zone between 0 and 62 megahertz. First thing you say, well, hang on a second now, but doesn't 4 meters go from 70 to 70.5 megahertz? How does that work? Well, the answer is it now uses undersampling. What it means is it uses the second Nyquist zone to basically capture or to receive 4-meter signal. Now, what this means, of course, is you have to use sampling. In this case, you need to use high-pass filter to basically chop off the signals below 62 megahertz. Because then those signals get into the mix, everything just get folded down to the first Nyquist zone, it all get mixed up when you try to recover the signal. Okay. However, there's an even bigger problem with all of this. That unfortunately, we have something called the broadcast band between 88 and 108 megahertz. And guess what? That sits right smack bang in the middle of your second Nyquist zone. So how is that dealt with? So this is what you have. You have your first Nyquist zone between 0 and 62 megahertz. You have your second Nyquist zone between 62 and 124. The first Nyquist zone has your HF, and has your 6 meters. Your 4-meter band sitting up here in the second Nyquist zone. Now the problem is you've got some very powerful transmitters up there between 88 and 108 megahertz. And if you don't do something about it, they're going to get folded down into your broadcast. That broadcast is going to produce an alias between 16 and 36 megahertz. And if anyone's tried operating an Icom 7300 close to a powerful F transmitter, you often see it coming through the band. I know I've got, because I have an awful problem with a transmitter up down in Wicklow. There's a local FM transmitter, and it blasts everything out. And I have to use filters and everything. You see, I've got filters on all my radios. It's the only way to stop them from coming through. So the way the Icom 7300 does that, it uses filtering. In fact, it uses lots of filters. It uses 15 filters, okay? So if you actually take a look inside your radio, that's what your filtering looks like. There's 15 filters built into the Icom 7300 to deal with aliasing. And that's aliasing in the first microzone and aliasing in the second microzone. So when you want to do your 4-meter work, you're basically chopping off everything below 60 megahertz, and you're also chopping off everything above your 4-meter band. You don't want to knock those broadcast up coming through, but if it's sufficiently strong, it will actually come through. I know I can sometimes see it come through. If you go to the white part of the band, you will actually see it coming through an FM transmitter. So that said, is filtering very, very important. So if you do want to use undersampling, you've got to use filtering. And as I said, Icom, it's a well-designed radio, and they've got plenty of, they've got a bank of 15 filters in there to make sure that the signal that comes in, and also more important, the signal that goes out, to answer to Joe's point there, is clean.
Are there any digital filters or
They're analog filters, yeah. Well, it have to be because these things are probably carried for 100 watts. So that's on the yeah. And they're all, so basically all those little red boxes there are all relays. So that's the Icom 7300. It's not remarkable radio, but it's kind of clever how it works. HF 6 and 4. 4 actually does uses undersampling to make it work.
It almost sounds as if 4 meters was an afterthought.
Probably was. Probably was. You probably find that easier when it was on the so the one that
just has to do 2 meters, which is big thing.
yeah.
It's a big downfall, yes.
Yeah. But that's another radio. Most people here probably have them, do they? So yeah.
It's the classic radio.
It's a super radio, yeah, I must admit it really is.
101 to it.
Huh?
101.
What's that?
I don't know. I don't know. 60.
Okay, so what I want to do anyway, before we look at some other ones, I want to have a look at some of the dongle devices. So, as I said, nearly all the ones in all the radio amateurs tend to have a USB connection somewhere on them. And this basically allows you to plug it into a computer, and then you basically have some sort of an SDR software application, a program running. And this does all the DSP processing. So remember, all we've done so far, and most of this talk is concerned with how do you get that RF signal down to a form of digital samples that has that capture the RF signal. Okay. But what we haven't looked at is how you demodulate that, all the filtering around. And this is an extra piece of DSP that's done. Now that would normally be done by a DSP chip. So for example, in your Icom 7300, there's a dedicated DSP chip. Well, do your USB, your LSB, your FM, your AO, and all the rest will be done digitally. But for those who don't do it in hardware, you can also do it in software. And basically, you run a program, and pick your program of choice. But that's what it does. It takes in IQ samples. So if you ever browse around on the menus and any of those SDR radios, you probably see the word IQ written, sort of IQ file input, IQ file output. There's some of them even actually display the IQ signals as well. Okay. So what happens is all those computer programs, okay, the applications, they take IQ samples from one of these things, or one of these things, or one of these things, and they do extra processing. Okay. Now I'm not proposing to talk about how to do that here because that's a whole extra talk. But also as well, they can do extra things as well. So the things like give you a spectrum, they give you a nice waterfall, you can have it recorded, you can play it back. You have memory and also the fancy features, the bells and whistles that generally go with it. But at a fundamental level, you take in the IQ signals from the dongle, the SDR front end, so to speak, and then do your demodulation, or vice versa. You can also do the modulation. You can modulate up if you're using a transmitter. Again, all the major operating systems are done as well: Windows, Linux, OS, Mac, and also increasingly that they actually do cross-platform. They do it on multi-platforms, so they have a version for Linux, a version for Windows, usually a version for the Apple Mac as well. And you probably recognize some of the names there: HDSR, SDR Console, SDR Sharp, or something known as RSPDx, SDR Plus, SDR Connect, which is the version Mark II of the SDR Uno, which is a much nicer interface. But as I said, it's still a very good SDR. There's also, if you're really curious, there's plenty of free software out there. There's open source software. For example, HamPi. It's an image you can flash onto an SD card, pop it into a Raspberry Pi. You have a whole suite of SDR radios and SDR applications. And more recently, there's a very powerful one now called DragonOS. So now the version for, again, it works for general Linux machines. It only work on 64-bit architecture, but the process with the machine, just to let you know that. But they have a Raspberry version of that as well called DragonOS Pi 64. Again, it's very, very powerful. So basically, it's some really quite remarkable software, and that'll do everything from packaged satellites, I think different TV to do as well, money, that type of thing. So it's quite powerful, a lot of applications in there. And the one problem is just slightly, it's a bit limited to the hardware. It really only supports the really, really popular software and really popular dongles, the RTL-SDR AirSpy and HackRF, and also the Pluto SDR. After that, just sort of on your own term. But they're taking the big three or the big four in terms of SDRs, which is the RTL, the HackRF, okay, the SDRPlay, and Pluto, which I don't have Pluto. Does anyone have a Pluto? No? No Plutos here? Okay. But they're the ones that want people tend to use. And finally, there's a really interesting one that I've been playing around for the last week or two. Open Web WRX. It's actually really clever. Again, it's a piece of software. You just download it, flash it onto an SD card, pop it into a Raspberry Pi, attach a dongle. Again, RTL, RSPDx, HackRF, and SDRPlay is the 4 to 10 to work with. But the nice thing is that's all you need to do. It basically has a web server. You just point your browser at it, connect to the net, point your browser at, and hey presto, you have a radio. You just click out, do everything from your browser. Remarkable. I've been playing with that for the last week or two now, and it's quite impressive. What's really impressive is there's an enhanced version called Open Web RX Plus. And what it does is it's got a whole range of built-in digital stuff. So it does all your FT4, FT8s, JT65, JS Core, 3DV, RISI, ADSP, SSTV, APRS, all done through your browser. It's really, it's definitely worth looking at, and it's still in active development, so it's definitely worth having a look at. Okay, so I'll talk to you maybe now if I set up some demos.
Yeah. You want to use the hover cam?
No. So the first thing I'm going to do is, so what I'm going to have a look at is the hack RF1. Okay.
We're going to stop your screen share now, okay?
What I was actually hoping to show you was two applications that one using the Raspberry Pi, and then two that basically are Windows-based. So the Windows-based because the only drivers available for them are Windows drivers. Okay, they haven't got a driver yet for the open source. So maybe just say something just about these two anyway. But they're so the first is the Hack RF. Launched 2014, developed by a guy called Michael Osman. If you ever want to have a look, there's some absolutely, he does a series of about 10 or 12 YouTube videos, and they're absolutely brilliant. They really are. If you want to really understand how SDR works, have a look at Michael Osman's YouTube videos on SDR. There's about 8 or 10 of them, but he covers every aspect. It's really well worth looking at it if you have an interest in this. It's been around in 2014. The last version was version 9 from 2023. It's half duplex, so this will do transmit and receive. Okay, it's an 8-bit analog to digital converter. Not great, but then again, it did come from 2014, and it will go from 1 megahertz to 6 gigahertz again using undersampling. Okay, it's software configurable in the sense that there's basically a series of filters can be switched in on now on it. This is the filtering bit. And they use the high-speed USB interface. And as I said, the nice thing about this is it is completely open source, hardware and software. It was basically a publicly funded project he developed. And so every aspect of this device is publicly available, right down to the printed circuit boards that are used to produce it. Okay, so it's well worth having a look at. It's a bit on the pricing side. It's about €300 for that, I think, even still, but it's very widely used and very, very widely supported. Okay, so it's definitely one to get if you want to have a really play around with stuff. There's a diagram. As I said, just don't worry about the detail. Just look at what you recognize. You see there's a microcontroller. You see, look, one Thomas there. Well, you lost it.
Share screen again there.
Well, as I said, don't worry about the detail. What the parts you recognize. And once again, what you see there, you see two mixers, quadrature carriers, local oscillator. The rest is just switches and filters. Okay. So that's really what goes on inside that. An analog to digital converter block, just the ADC and DAC. And that's what's inside that. Again, this is all absolutely publicly available. So that's a beautiful. It's a truly open project in terms of hardware and software components. Okay, so as I said, it does transmit and it does receive. And again, it's drivers for Linux, Mac, and Windows. There's a HackRF tool command line, which types stuff in and control it directly from your keyboard if you like. And it works with virtually every SDR radio out there, so it works with a software radio. The new radio, SDR Sharp, Console, GQ or X. Again, because it's so old, it's virtually everyone supports it. It's a lovely little radio. Not just, the performance isn't great, it's only 8-bit, but no, that said, it is a remarkable radio in terms of how well it's supported. Then, of course, everyone's favorite, RTL-SDR Dongle. Again, beautiful business, low cost, it's about €25. Again, 8-bit analog to digital converter, sample up to about 2.4 megasamples. So you're looking at a chunk of spectrum, about half that, about 1.2 megahertz is a chunk of spectrum you can have a look at. The later versions, version 3 and version 4, will actually go down the direct sample from down to as low as 500 hertz. The original one went from 24 megahertz to roughly about 1.8 megahertz. It's just to watch out for it. It's as many people make these, by the way, but probably the most reputable ones are produced by the company RTL-SDR blog. A bit 5-10, maybe 5-10 euros more expensive than anybody else, but they are worth it because they are popping filter and they're used quality components. The latest version.
Sorry, Mark. Can you go back to the slide?
I hope to have one with you. I have it on order from AliExpress. It hasn't arrived yet, but hopefully it will come shortly. But it basically uses a slightly different radio tuner. The reason why this is so cheap is it uses bog standard chips that were developed for digital television. So it uses quite basic components, low cost, mass produced chips, and that's why this is so cheap. So as this is what the circuit looks like. Again, don't worry about the detail. What parts you recognize? Well, the two recognize there: analog to digital converter, 2 mixers, a sine and a cosine input, IQ signal representation. That's all you need to know. 2 parts here, samples. And this is what the new version 4 looks like. It has a black body rather than a sort of silvery body, and has a new improved tuner chip. And I said it's currently out now. And this is actually going to be limited run because they don't make these chips anymore. So when this is gone, it's gone, as they say. So if we have an opportunity to get one, definitely can. I have mine on an order. Hasn't arrived yet. Then, of course, there's the SDRPlay. A lot of people have this radio. It's a lovely radio, actually, the RSPDx. It came in November 2019, 14-bit. Goes from 1 kilohertz up to 2 gigs. It allows you to basically take a look at a chunk of spectrum at 10 megahertz wide. So that's a much bigger chunk of spectrum. It has notch filters where you can tune out broadcast bands. And as I said, it again has a classic USB 2.0 Type B socket. Once again, in terms of circuitry, the reason why it does is, again, it uses 2 chips that were developed primarily for digital terrestrial television. There's a tuner bit and a bit that basically looks after the analog to digital conversion. And as I said, you can basically take a look at the specs for those 2 chips. Again, no need to worry about the detail. Look what part you recognize. Again, you see there the mixers, quadrature signals in terms of the multi-mode or tuner chip. Again, this basically does analog to down conversion, and then the other chip basically does the analog to digital conversion. So one does the tuning, down tuning, analog to digital conversion. Hey presto, out the USB port, you get all your digital signals, your digital samples from your RF signal at the input. Okay.
Maybe capable of transceiver approach because the one you mentioned earlier.
Yeah, this one does do it. This device also does it as well. It just depends how much circuitry goes into the box, you know. It's minimal. It's tens of milliwatts. Tens of milliwatts. So tens of milliwatts is always. So as I said, the reason why these devices are reasonably priced is because they do use, you know, very, very popular chips that are developed for the digital television market. And of course, the SDR Uno, probably a lot of people recognize the original. One of the main reasons why this was so popular was exactly was a lovely front end to the SDR Uno. It's a bit dated at this stage, you know. It's now been replaced, it was only released back in August. The SDR Connect, which actually is a much, much nicer platform. It's multi-platform. It can work to have a version for Linux, for the Mac, and for Windows. It does require a 64 architecture machine, and also as well, it can be done as a remote server, so you can set up your radio, and then you can basically monitor it wherever you like across the network. So you can do remote monitoring of your network as well.
They usually do something for Black Friday, Cyber Tuesday, or Black Tuesday, have a deal.
Who do they? Do they?
Yeah.
SDRPlay. Okay, cool. Yeah. Well, certainly, if anyone has been using SDR Uno machines up to it, have a look at SDR Connect. It's a much cleaner, much neater. Those horrible windows that they have in the SDR Uno, you have to position it. Yeah, it's all fixed. It's all Docker. It's coming from 2 years. I know. Yeah, they arrived in August. It's still a beta version, but it's actually spread out the playing for a while. It's lovely. It's so much cleaner and neater and less cluttered. And as I said, you can also close down windows and hide stuff. It's much nicer. Have a look at SDR Connect. It is freely available from the SDRPlay site. Okay, so we'll have a look at we do a demo on this one. This is a nice one. This is an extraordinary device. One of my students brought it back from China. Because I got direct from the supplier, so to speak. So this is direct sample SDR. It was released in February 2020. It's a 16-bit analog to digital converter. So it's as good as it gets. It blazes along at about 130 megasamples per second, so it's fairly fast. Okay, has got a built-in tunable attenuators and tunable amplifiers. It gives us a dynamic range of about 96 dB. It also has two inputs, one for HF and one for VHF. Currently, the only works on Windows, and there was a driver developed by an Italian guy, Oscar Stella, who developed a driver for it. It's available on if you go to GitHub, you can download it. The thing about it is, it's very fast. There is no processing in this. It's just a very fast front end and a very fast analog to digital converter. It uses a USB 3 port. That's the port with SS written by the way on your PCs. And so it does work with a number of radios. As I said, there's no digital down converter. All that needs to be done in your PC. As I said to you, this is why these start to take off, because the PC power starts to take off as well. But it works with most of the software within reason. HDSDR, SDR shop in a console. It needs a very powerful PC. Okay. In fact, even with this machine here, I can't run this at full speed on this machine here. It just kills the machine because there's no processing. This is just a very fast front end and analog to digital converter. So what I might do, I might just show it how it works. So I plug it in here. If you have to plug it into the SS port, because it's an USB 3. Okay, there we go. And connect it up to there's a built-in filtering, so I don't have to put a filter pump down on this. So that's straight into the right. Okay, so I'm going to roll it with the this is reorganized all my icons for me. There we go. So the first thing you do is you have to select the driver. So it's developed by the Italian. So what this is basically HDSDR. And what this is basically currently doing at the moment is this is basically sampling. So the beauty about this is this can actually sample the entire HF band. Let's say that's now going from just below 1 megahertz right up to 30 megahertz in a single sweep. So you can basically look at the entire. You can basically have a look at the entire HF band because this thing is sampling so fast. This thing is basically sampling at 130 million samples per second. Okay, you divide that by 2, this was 65. So no problem accommodation the full 30 meg of the HF band in a single sweep, or a single set of samples. So that's absolutely remarkable if you think about it. It's really astonishing. It's very fast. This is the only program that I can actually do this with because with quite any of the programs at that particular sampling rate, that's a very lightweight program. If you use any other ones, it will actually struggle and the base machine will lock up because it just can't handle the computational load. But it's actually remarkable. It's very wide band. They said you can take the entire HF band with a single picture. Quite incredible. And that obviously blew me away when I first saw that. This must be it's quite remarkable. So that's using HDSDR. You can also use other radios with it as well. one of the nicest, actually, one of the best designed SDRs is SDR console. This is it's beautifully designed, I must admit, in terms of the layout and the thinking behind it. There's been many, many years in development, but it's so this is a SDR console, and it's free to download, although the guy who developed it does ask for donations. So if you do use it regularly, it's probably going to need to contribute to the development effort and the development charges. Again, it's very, very nice. It does also stuff, has a waterfall display, a nice S meter, a lot of very fancy features there, filtering and so on. That's one I don't use it all that much, but don't tend to use Windows, but it's definitely one of the better ones to use. The other nice one to use is there's another SDR program. It's used for RFI, sometimes known as SDR Sharp. It's the radio that was developed to accompany the RFI SDR radio. But that's a very nice one. It's really nicely laid out, and it's very, very flexible. There's a huge number of things you can do with it beyond just, this is like overdown the business get added on. There's lots of extra stuff you can do with this, and you can have up to 8 different receivers running on it at the same time. So it's actually very, very flexible. So if you're into monitoring multiple bands or at least multiple signals at the same time, it's the one to use. And that basically is SDR console. I'll show you the other one as well. If I was using, I would tend to use the SDR Sharp. I think it's a nicer one. It's just purely aesthetics, nothing else. That's there's SDR Sharp now. This one, Porty, I have to be careful with this one because this is quite a heavy SDR. And if I did run it at full blast, it would probably not work. So I genuinely going to drop down the sample rate down from so I have this, that's going to be on the high side. Let's try 4. Okay, just try that. The signals can be low antennas there. But not too bad, VHF. Yeah. Okay. Okay. This is how. I want to see if it will. Right. Okay. So hopefully I have there. It's a little pound pretty quiet. Oh, sorry, I know playing part. I know these numbers. Yeah, so we have to go to the settings. I need to turn up the turn up the attenuator. So there you go. And that's currently listening in on our friend there, FT8. Okay. So that is the HD. That's big part. That's say that one. That's RSPDx, which is that's sharp. That's the SDR Sharp one. Okay, that's quite a nice one. So they're probably the 3 popular ones, and they're all pretty well designed. They all work really, really well. They tend to work with sort of a broader range of devices. So I see the whole list of them there. And as I said, I was using this particular device here, which happened to careful because it is so powerful it will overwhelm your PC. If you're careful.
So that's role will that have surveillance.
Yeah.
It is really.
It was cool, and then there's a certain pleasure in having the whole HF spectrum straight into you. Yeah. Yeah, well, you're right. A lot of this is the military buy these things up. Yeah, thousands. They just record whole swathes of spectrum from signals. Okay, so that is the. I just want to say something about this device here. This really is a really quite remarkable device here. This really is where radio is actually going. It's I have a slide on. So really what it is the entire radio in the box. There's an SD card that you flash. You plug it in there. There's an onboard processor. There's a 16-bit analog to digital converter. It's very, very fast. It has accuracy. Okay. At least have a little fan running up because it doesn't provide a lot of power. But it's actually absolutely remarkable, and some lovely software developed as well. So let me say something about that. It's happening off control. I'm going to show this again, internet.
Yeah.
If I can.
Have our cameraman here.
So maybe let's finish off this TRX duo. Again, this is a dual channel. It goes transmit and receive. It's got two transmit and two receive. Okay. It does 10 kilohertz to 60 megahertz. It's a digital down converter, digital up converter. It's got two antennas for transmit to receive. It's a 16-bit HD converter at the receive. At the transmit, it's only 14-bit at 125 megasamples per second. Divided by 2, that gives you a 60. Okay. It's a Chinese clone of a radio called RSPDx. It may have come across a presentation device, but it's actually half the price of the RSPDx. This is about €300 compared to the RSPDx, which is about €600 or €700. But the beauty is it has a Xilinx zinc. Okay, remember that before? The zinc system on a chip inside. It's a dual-core processor. It's got onboard RAM. You basically flatten an image onto an SD card, pop it into the back, power up. There's a connector here on the back, an Ethernet connection. It's an Ethernet connector, so it's really, really fast. And then presto, you can basically configure the unit to anything you want to. This is what MKII, the company that originally worked on this, actually did. So,
You just share a screen there again, Mark. Yeah. That's very good. Yeah.
it's like the three tiers or jigs or duo. As I said, it's very, very powerful. It's really where it's going at the moment in terms of where radio is. So this is close to what maybe commercially available, like with the Icom 7300 and what you do on a single board, you know. The nice thing about this is it basically it has an onboard browser. So what you once again is over the internet or over your local network, you basically point your browser at it. There's a whole series of applications. So it does everything from oscilloscope, spectrum analyzer, DNAs, transceivers, you name it. Click on the application, flashes the FPGA to be a VNA, to be an oscilloscope, be a spectrum analyzer, to be a transceiver, be a whisper transmitter, be an FPGA transmitter, doesn't matter. And the nice thing is applications have been developed all the time. So there's a special folder called Marketplace. It's always worthwhile going in there every so often to see what's new. So people are always just adding stuff into it, and you basically can find in there occasionally. Now, in particular, there's a series of applications developed by a guy called Pavel Denon. Pavel Denon. He developed a whole series of ham radio applications that are available as well. And basically, he's flashed them all onto a distribution based on Alpine. And the latest version is on the 5th of July. 2023. It has SDR receivers, SDR transceivers, has a whisper transceiver, has an FT8 transceiver. I have this running, by the way, 24/7 as my FT8 and also as a whisper receiver. And it simultaneously monitors 8 spans together because it's so powerful, it sucks in the entire HF band and basically takes out 8 frequencies where you find whisper and processes them and pushes them all up to whisper rocks, where you can see what's happening in terms of what's the reception like of the application of voting actually whisper. So when you point your browser at it, you get a menu, and you just click on what you want. You want to click an SDR receiver, just click your browser and it turns into an SDR receiver. Click on a transceiver, turns into a receiver. Click on an FT8, it becomes an FT8 device. It's that simple. No hardware, no changes. Every time you do that, it just reflashes the FPGA, and hey presto, you have a different type of radio. Absolutely remarkable. It really is. It's really astonishing.
Mark, we'll have to wrap it there.
No problem.
Yeah.
So what's it? So to summarize, 3 fundamental concepts. Okay, all functions digital implement, all functions implemented digitally in terms of digital down conversion and up conversion. Sampling theory, we just need to know 2 things. Nyquist zones and aliasing, and also IQ signal representation. You'll find it everywhere. Every SDR uses it. In terms of design, you have a look at transceivers with the Icom, you have a look at dongles, you have a look at FPGA devices, such as the TX or Duo, but the Pluto also is an FPGA device. Best of all, there's tons and tons of free open source software out there, so you have no excuse not to go out and play with it. So there you go. Hard to get all the demos, but thanks very much for your
time. One question from online.
Yeah, I've got a question for you, Mark.
It's
if-
just from
if
Rob.
you
He's
don't
been
mind.
wanting to ask a question there for the last hour or so. If you just can you speak there now, Rob?
Yeah, can you hear me? Can you hear me?
No sign of Rob. Okay, maybe just one question from the audience, and then we'll wrap it.
terms of the high-level parameter like sensitivity and selectivity and the overshoot, is it comparable performance or is it all down to the completely converter?
It's all down to the analog switch converter. It's also all down to the, I suppose, the digital signal processing. No, I have not talked about digital signal processing. And it's like everything else, it comes down to performance against computation effort. So if you have a very, very powerful PC, you can run very, very powerful filters and very, very powerful whatever. So you have very good builds. But if you're sort of compromised by the performance of your processor, you will not be able to have very, very good filters, very sharp filters. Like so, really, really good filters could be left order 30 filters. Now to do that in DFP requires a lot of number crunching. Unless the PC is up to it, you won't be able to do it. So the bottom line is, it really comes down to your computing platform. If you have a powerful computing platform that can handle it, you have radios that are much, much better than an analog radio. So the fact that you will have a requirement for a very, very powerful processor to do all that. Yes.
Okay.
Thanks, Mark.
Thanks so much.
Can you hear me, guys? I
Thanks,
had
everybody.
a question earlier.
Thanks, guys. So, I think that's sort of yes.
That's me. Okay, guys, thanks for coming. We're stuck against closing time here at the community centre. Get kicked out at 9:30. I'm going to put the video up on YouTube. You can always message us on Twitter or on YouTube, and I could get questions to Mark. In terms of come to the club here this Tuesday night, you can join us on Zoom or you can come in person. Okay, so listen, thanks again for coming along. Have to power down and get out of here. Okay, cheers. Derek with the cameraman.
Derek.
Sorry, thanks for coming by.
Thanks, Adrian. Thanks, Mark.
So,